Hello friends, the topic for this video is Floyd Warshall's all-pair shortest path algorithm. The problem here is you are given a graph G like this with set of vertices V and set of edges E. You are given a weighted connected graph. So you are given weights for all the edges as shown here in the figure. Your job is to find out the length of the shortest path from each vertex to all other vertices. So we have already seen how to find out the shortest path from a single source to all other vertices in our video lecture of Dijkstra's algorithm. But in this algorithm, you are trying to find out the shortest path from each node to all other vertices. So from A, you are going to find out the shortest path to B, C and D. From B, the shortest path to A, C and D. From C, the shortest path to A, B and D. From D, the shortest path to A, B and C. So for finding the shortest path from a given vertex to all other vertices, we are going to use dynamic programming approach to solve this problem. Let us take this example to understand all-pair shortest path algorithm. You can consider the vertices as cities and your job is to find out the shortest path from each city to all other cities. So let's represent this graph as a matrix called as adjacency matrix. So there are 4 vertices in this particular graph. So we'll create an adjacency matrix of dimension 4 cross 4. 4 rows and 4 columns. Now let us try to fill up this matrix. If you can see here, there is no self loop on A. Similarly, no self loop on B. So A to A, the distance is 0 or the cost is 0. B to B, the cost is 0. C to C, the cost is 0. D to D, the cost is 0. Now let's see if there is a path from A to B, direct path. A to B, there is no direct path. So if there is no direct path, there is no path from A to B, so we'll mark it as infinity, a very big number. A to C, it's 3. A to C, it's 3. A to D, there is no direct path. We have a path from D to A, but not from A to D, so it's again infinity. Similarly, B to A, it's 2. B to C, again no direct path, so infinity. And B to D, there is no A's, no connection, so again it's C to A, there is no direct path, so infinity. C to B, it's 7. C to D, 1. D to A, 6. D to B, no direct path, no path from D to B, no A's from D to B, so again it's infinity. D to C is also infinity. So this is our adjacency matrix, also called as weight matrix W. The objective here is to find out the distance matrix. The distance matrix D is a final matrix, something like this, which will contain the shortest path from each vertex to all other vertices. We are going to develop the distance matrix gradually, starting from the adjacency matrix. Initially, the distance matrix D0 would be equivalent to our adjacency matrix. We'll start with the same matrix first. Then we'll use the value of D0 and then we'll calculate D1, distance matrix 1. Then we'll calculate D2 and so on until we find out our final distance matrix. While calculating D2, we are going to reuse the values already calculated in D1. While calculating D1, we are going to use the value already calculated in D0. D0 is nothing but same as W. So here this is dynamic programming solution because we are going to reuse the values. While calculating the intermediate distance matrices D0, D1, D2 and so on, we are going to introduce a new intermediate vertex. So while calculating D0, we assume that there is no intermediate vertex to find out the final path. While calculating D1, we assume that there is just one intermediate vertex and let's say that's A. So only A can act as an intermediate vertex to find out the shortest path. While calculating D2, we assume that we have two intermediate vertices, that is A and B. While calculating D3, we assume that there are three intermediate vertices, that is A, B and C. While calculating D4, we have four intermediate vertices, that is A, B, C and D, and D4 would be our answer, that is equivalent to D. So now let us see how to work on creating these intermediate matrices and finally create the distance matrix D. Initially, distance matrix D0 is equivalent to the weight matrix W. So in this distance matrix D0, as this is 0, that means we have 0 or no intermediate vertex. So we are only considering the direct path from the source to the destination and not considering any intermediate vertex. Therefore, D0 is equivalent to W. Now let's calculate D1. To calculate D1, we will consider just one intermediate vertex and let's say that intermediate vertex is A. Now what do you mean by intermediate vertex is? Now A is allowed to act as an intermediate for finding the distance between source to destination. A can act as a intermediate. This is what it means. So I have already told you to calculate D1, we are going to reuse the values already stored in D0. So if you are calculating D1 and your intermediate vertex now is A, we are introducing A now as an intermediate vertex, you remember one very important concept. There will be no update to the row which contains A. This is row with A and column with A. So there will be no update on this particular row and this particular column. So you can just copy the values here as it is. So this should be 0, infinity, 3, infinity copied as it is. Similarly 2, infinity and 6 copied as it is. Now let's see B to B. B to B obviously it's 0 because there is no self loop. So B to B, C to C and D to D would be 0. Now let's calculate B to C. So if you look at this table D0, B to C, the distance was infinity. That means there was no direct path from B to C. But now if I have introduced A as an intermediate, do I have a better path? Yes, if I go from B to A, the distance is 2, and if I go from A to C, the distance is 5, right? So now I get 5 as a new path from going from B to C via A. As 5 is less than infinity, I need to update this to 5. Now let's talk about B to D. B to D, there was infinity, no direct path, but if I go via A, can I reach D? B to D, I cannot reach D via A also, directly via A, only via A. So this is still marked as infinity. C to B, C to B, it was 7, but if I go via A, there is no direct path from C to A, so there is no chance to update a path from C to B via A. So again this is copied as it is. So C to B is 7. C to D, C to D previously it was 1 and I don't think there is a better path via A and there is no path to go from C to A, so it's still 1. And D to B, D to B via A, previously D to B via A was infinity because there was no direct path, right? So but D to B, let's go to B via A. So D to A, so D to A, the distance is 6 and from A to B the distance is, you don't have a direct distance from A to B, it's infinity. So 6 plus infinity is still infinity. So it was infinitely before and now also it's infinity. So there is no update, copy as it is. Now let us calculate D to C, the last one, D to C, this one. So D to C, previously it was infinity. D to C was infinity previously. Now if I go via A, I get a new path. D to A is 6. So A to C is 3. 6 plus 3 is 9. So, and 9 is less than infinity. 9 is less than infinity. So I get a better path. So I get an update. So in this particular, no, this is my D1. So in D1 I got a new updates. This one highlighted here. This one B to C 5 and D to C 9. Now let's calculate D2. Now to calculate D2, as this value is 2, we have now two intermediate vertices, that is A and B. We can choose A and B as intermediate vertices. But we have already stored the path. If we choose A as intermediate, that is stored in an intermediate distance matrix D1. So to calculate D2, we'll reuse the values already stored in D1. As I have told you, now we are introducing a new vertex B. The values of row B and column B will be copied as it is. So row B is 2, 0, 5, infinity, and column B is infinity, 0, 7, infinity, infinity, 0, 7, infinity, and you can mark all the diagonals as 0 because there is no self loop. So all the remaining values we need to calculate now. Now I can choose A, B also as an intermediate. Let's calculate AC. AC, it was 3, via B there is no path, so AC is 3, no changes. AD, AD was infinity, via B I cannot go to D, so again it's infinity, no changes. C to A, C to A, previously it was infinity, but via B, C to A via B now is 7 plus 2, 9, and 9 is less than infinity, so this is a update, this is 9. Via B I can go to A from C, so C to A via B, 7 plus 2 is 9. C to D, C to D it was 1, again if I go via B or via A I cannot get a better distance, so copy 1 as it is. D to A, D to A it was 6, if I go via B I can go to B from D, and so this is copied as it is, 6, no changes. And D to C, D to C via A, D to C was 9, right? Via B I can't go via B because there is no path from D to B, so again it's just copied as it is, this is 9. So this is my matrix D2. Now let's calculate D3. As this value is 3, I have 3 intermediate vertices, that is A, B and C. Now if you can recall, I have already calculated the shortest path using A, B as intermediate vertices, that is D2. So here I have used A and B as intermediate vertices. Now to calculate D3, I have introduced a new vertex C. So I am going to reuse the values from D2 to calculate D3. As now here I have introduced a new vertex C, I will just copy the row C and column C 9701 and 3509 as it is, and I will mark all the diagonals as 0. So now I need to calculate distance from A to B. The distance from A to B, if you look at D2, is infinity. A to B there is no direct path as of now, so A to B as of now the distance of A to B is infinity from this particular table. Now I have introduced a new node C. Now if I introduce a new node C, do I get a better path to B from A? So A to B via C, that is A to C is 3, so A to C the distance is 3, and C to B the distance is 7. So I can write the distance from A to C is 3 and the distance from C to B is 7. So if I add them together, that is 7 plus 3 is 10. So I get a better distance. 10 is less than infinity, so I have to update. So this is 10. A to B is 10 now. Alright, so what I have done here is I have found out the minimum of this and this. Whichever is minimum, I am storing that as my new distance. because this is the shortest path problem. I need to minimize the distance. Now let's calculate the distance from A to D. So distance from A to D, if you look at this, A to D is infinity, no direct path. So A to D, there is no direct path. So distance from A to D as of now was infinity, right? Now if I introduce C as an intermediate, A to C is 3 and C to D is 1. So A to C is 3 plus C to D is 1. So 3 plus 1 is 4 and this is infinity, right? So which one is minimum? Minimum is 4. So the new distance from A to D would be 4. This would be via C. Alright, so I get a new update here. This becomes 4. So now if you can look at this, this is the formula for finding the distance. The new distance, this is the new distance that is going to be stored in D3 this is the old distance that I have already stored in D2, okay, and this is the distance from A to C, this one, and this is the distance from C to D. So this is a new distance via C, which is 4. So 4 and infinity, whichever is minimum would be the new distance. So new distance is 4. So this is the formula for calculating the distance. Now let's calculate B to A. B to A, it was 2, and via C, B to A via C, no distance, so it is 2, no updates. Now let us calculate the distance from B to D. The new distance B to D is going to be the minimum of the old distance. This is the old distance B to D, and the distance via, this is the distance via C. Alright, so distance, old distance B to D was infinity, comma, distance from B to C, I'll look at this table, B to C 5, I'm going to reuse the value, plus distance from C to D is 1, so 5 plus 1 is 6, so infinity comma 6, the minimum is 6, so I got a new distance from B to D, that is 6. If you look at this diagram, B to D, 2 plus 3 is 5, 5 plus 1 is 6. So I get a better distance, less than infinity, so I update. Now the distance from C to D is 1 and there is no other better path, so this is 1 as it is. Now let us calculate the distance from D to A. So from D to A, the old value D to A is 6, the previous distance, but if I go via C, D to C, if I look at this table, D to C is 9 and C to A is also 9. So the old distance was 6 and the new distance is 9 plus 9, that is 18. So old distance itself is lesser than the new distance via C. So I do not update and keep this 6 as it is. Let us calculate the distance from D to B. The old distance from D to B, if you look at the table, is infinity. But if I go via C, D to C, the distance is 9, and from C to B, the distance is 7. So 9 plus 7 is 16, is less than infinity, so I update and this becomes 16. Now D4 is the last value of distance matrix that we are going to calculate. As here we have 4 intermediate vertices. All the vertices can be an intermediate vertex now. A, B, C and D, which we have introduced just now. So considering D as an intermediate vertex, what would be the distance matrix? So for this, D is the intermediate vertex, so I'll just copy all the corresponding row with D, corresponding column with D as it is here, 4, 6, 1, 0, 6, 16, 9, 0, and all these diagonals is made as 0. Now distance from A to B is 10, is not updated. This is 3, not updated. This is 2, this is 0, this is 5 and this is 6. You can investigate on this, they will not be updated. Now let's see C to A. So C to A, previously C to A was 9. Now via D, what is C to D? C to D is 1, and D to A is 6. So 6 plus 1 is 7. 7 is less than 9. So I got a new path from C to A via D, which is 7. 7 is less than 9. So I'll update this. Similarly, let's calculate the distance from C to B. The old distance from C to B was 7, and the distance from C to D is 1, and from D to B is 16. 16 plus 1 is 17. So obviously 7 is less than 17, so I do not update and copy this 7 as it is. So this is my final distance matrix, and this is called as distance matrix D. Now this distance matrix will finally give us the shortest path from each node or each vertex to all other vertices. Like from A to A, obviously it's 0, A to B is 10, A to C is 3, A to D is 4. Similarly, B to A is 2, B to C is 5, B to D is 6, and so on. So this is our final answer. To calculate D4, we have reused the value from D3. To calculate D3, we have reused the value from D2, and so on. So because we are reusing the values that is already being calculated, this is a dynamic programming solution. Now let's look at the algorithm for the same. In this Floyd Warshall algorithm, we are assuming that adjacency matrix W is our input, V is the set of vertices, N is the length of W or number of nodes or number of vertices in the graph. We are going to create a distance matrix D of dimension n cross n, which we are doing it here. We are going to update this distance matrix through this loop. But before doing that, we'll assign the adjacency matrix to the distance matrix. So we'll make a copy of W and place it in D. We have seen this in an example as well. So now I'll explain you the significance of this loop. So U is our source and V is our destination. So we'd like to find out the shortest distance from U to V, and we may have an intermediate X. This is our intermediate, right? So we may have one more path from U to X and from X to V. So what you are doing here is U to V, distance from U to V is this one, and distance from U to X is this one, and distance from X to V is this one. So whichever is minimum, I am updating my distance matrix, and I am doing this for all the source, all the destinations, including all the intermediates. So to talk about the time, this is the algorithm. To talk about the time complexity, there are n number of vertices, so this loop will run n times, n times, n times, nesting of 3 loops, so it's of order of n cube. This is the time complexity of Floyd Warshall's shortest path algorithm. So that's all for this particular lecture. If you have any doubts on this topic, please comment on this video. Thank you.